Hello, everyone. This is Professor Ma, and this is the sections on infinite series. So, infinite series means adding infinitely many numbers, try to get an answer. And here's examples of we are able to add infinitely many entries, but you wind up with a finite answers. So for instance, we take a rope and we cut away half of it, and then left is half. And then we cut away half of that, and what's left of quarters is a quarter. Okay, and so on, so on. Okay, and if we ask the questions, um, says what if we were to add up all the pieces that we cut off, one half, one quarter, one eighth, and so on, so on, and then put them all together, and then all the cut away altogether is going to be one. In other words, there will not be any numbers that sits over here that's remained. And it's the argument for that is sooner or later, the cut is going to surpass these numbers, whatever number you name, and the bits that's left is going to, if you cut it enough times, it's going to pass that point which you think it's going to stay, remain without being cut. And there's no such point. So that's the basic gist of the argument. Okay, and so this demonstrates that we can add infinite many bits and wind up with a finite answers. Okay, this is very important conceptual things to accept. But on the other hand, if I add up infinite many constant, one half plus one half, C is a constant over here. Suppose I'm adding one half plus one half plus one half. I keep adding one half, and this of course then it goes to infinity. So adding infinitely many positive numbers. So this is where we're going to first start looking at adding everything being positive. There's no point adding zero. So let my everything is positive. There are only two possible results. Whether the sequence come to an answer, like the ones up here, equal to one. We call such series, or the series add to one, and then we call such series convergent. It come to a point, sum. Okay, and as opposed to convergent, of course, we have the diverging series, which means it adds to positive infinity. And adding infinite number is not going to swing wildly. It just going to keep accumulating toward infinity. Okay, so that's what a diverging series is. And to define what converging diverging series more carefully, we do the following things. For every sequence, it's easy to associate the series. Okay, every positive sequence. Suppose I was sequence over here, A1, A2, and all these are positive number, and so on, so on. Then of course it relate to a series that is adding them together. And that's a series related to all these sequences. So the infinite series of adding the sequence is the series associated with the sequence. But on the other hand, for every series, B1, B2, plus B3, okay, this a series is also associated with a sequence, and that's kind of, that is its partial sum. So the sequence, the sum of the first entry, then the second terms of this so-called partial sum series is the sum of the first two entries. And then so on, the sum of the first three entries, we call that partial sum S3, B3, and so on, so on. Okay. And what's why do we talk about this partial sum, the sequence of partial sum? That's how we define the series converge or diverge. So a series converges, okay, if this partial sum as a sequence diverges. And we know what a sequence converges. We know what a sequence converges means. So if the partial sum converges, okay, so and this is a definition of exact definition of what we mean by a series converges. A series converging, this infinite sum, quote unquote, this dot dot dot. We say this converges if this sequence of partial sum S1, S2, S3, Sn converges. Again, we're going to assume everything is positive. So when we look at the partial sum, it's going to be a positive increasing sequence, assuming there are no zeros. Okay. Yes. Mm-hmm. Now we come to questions first, and the question of convergence and divergence. A bit before that, let's talk about what kind of series we can add, actually get our answers. And basically, there are only two type of series that we can add algebraically and get on answers. All the rest, they are a lot trickier. You have to get a lot more detailed mathematics, sophisticated harder mathematics to deal with. But these two can be gotten. So one called a geometric series, and the other one is called a telescoping sums. These two type of series are the only ones we can get the answers easily. Let me say easily. Okay. The geometric series came from these multiplication patterns, and if I keep going and if I do it again, and we have these multiplication patterns. Okay, and what part the part we're interested is this part. That's the geometric sum. Okay, the sequence, geometric sequence. By the way, the geometric sequence, the sequence will look like that. It looks like you keep multiplying, like for 1/3 multiplied by 1/2 will be 1/6, multiplied by 1/2 will be 1/12. So will be a sequence where you multiply by a common number R. Okay, so in other words, your geometric series look like this. But if you factor out the A, and then the geometric series means you're adding R squared, R cubed, and so on. So this part is the part that shows up in these algebraic formulas. So if I isolate that sum, we can write that sum. Okay, and be careful. And we start out with n equal to, take the one and yeah, and n equal to k z k equal to 1 to n. That should be filled in there. Okay. So I get this geometric sum formula. In particular, the case we are interested in when this infinite sum will exist is when the number R is less than 1. And the absolute value less than 1. Why? Because if the absolute value is less than 1, then these terms as this add more terms, then this R to the n will go to 0. Then the sum, the infinite sum, will goes to 1 over 1 minus R. And so this is the geometric formula, summation formula, provided the number R absolute value is less than 1. Okay. So here's an example. And we start over here and go to 1. So we write out a few terms. And this is a geometric sum. And the way to deal with this sum is factor out. Notice we want this formula to start out at 1. So r squared. So right now we don't have 1 in the front. So we factor out the first terms, make it 1. Okay. So, and that's the geometric sum that we can use a formula. And in this is the case where r is equal to 1/3. So use the formula, and then we have the sum. And sometime, and we have a problem with it. It's basically a geometric, but the kind of the index is shifted, and you have to make it fit the formulas. There are a couple of ways to do this, and this over here is we try to start the sum at we're going to shift the entire sum, the index, to k star k equal to 0, because in the formula we require that we start out with the first term to be 1 plus r squared. So if we want to match that formula, we shift we can do this shifting of index. So we start out with k equal to 0 as required. I'll let you go through the change of index on these particular settings. But on the other hand, you can do as before, factor out, write out a few terms. It's basically a geometric sum. So you will factor out basically the first term. Okay, it's going to be geometric because if you look at this carefully, you basically multiply 2 minus 2 to a power divided by 3 to a power. Okay, can you adjust easily into a geometric? So you take out the first term, and you wind up with the geometric sum of with r is equal to minus 2/3, and then you can then use the formula and do the infinite sum. Okay, this is one type of sum we can sum, the geometric, where the absolute value of r is less than 1. And another type of sum we can sum is we call telescoping. And the reason we call telescoping is because when we start writing out the terms, and the terms actually cancels out. Okay, and they cancel out, they skip terms and cancel with terms like maybe 3 terms down below, and they keep doing this cancellation. Basically, the entire tail parts cancels out. Like for instance, here. If I put n equal to 1 in here, I get 1/3, and put n equal to 1, I get 1/3 minus 1/5. Now when n's 2, I'm going to get 1/4 in the front, and then put 2 in here, I'm going to get minus 1/6. And when I put n equal to 3 in this formula, I'm going to get 1/5 minus 1/7. I'm going to do one more, and that 1/3, 1/4, 1/5, 1/6 minus 1/8. Okay, by this time you can see what we mean by telescope. By the way, this is a 6. Okay. Here's where you start telescoping. The 1/6 and 1/6 will cancels out. Minus start showing up again. Next term is going to be 1/7, and the 1/7 and the minus 1/7 and minus 1/9. And you find out that as if I keep writing the 2 sum, and all the terms gets canceled out. Okay. Again, the skip terms will cancel. 1/5, 1/5, 1/6, 1/6, 1/7, 1/7, 1/8, 1/8. So in other words, all these stuff are gone. You're only left with these 2 terms, and that's a sum. And sometimes we don't write the formula like this. Sometimes we, instead of giving the telescoping as 2 components, which if you write it out, you can clearly see the telescoping where things cancels out. Sometimes we put them into one fractions. I believe this is 2 over m plus 2. Okay, so m plus 4, 1/2 maybe. Yeah, 1/2. A minus n, if I put them together, 2, 2, 2, 2, 2, 2. So sometimes this problem will be phrased as, if I expand this, would be phrased as n squared plus 6m plus 8. So if a given problem like that, if this is a telescoping problem, then this would have been, you would be able to factor this into difference of two linears, and you can start with a telescope. Okay, like this. Okay, so this is from partial decompositions, partial fraction decompositions. So you can break it up into two fractions. And we find out that you can break out the partial decomposition as this. And notice now, the 1/4 doesn't matter, we can take that out. Basically, we are dealing with m minus 3 minus m plus 1. And where do we start with the number n equal to 4? Okay, so if you start plugging into 4 and n equal to 5, and you start writing out term by term, equal to 5, equal to, so on, so on. You write them out term by term. You pretty soon you find out things start cancel all the ones in the back. That's what you're going to get left. Okay, so these are telescoping sum, and these are the only two we can arrive at an answers. What it is, the sum, what the answer of the sum is exactly, through without fancy mathematics, through basic algebra. Okay. Now, next we will talk about how to determine things that we cannot sum to an answer. Then how do we decide conversion or divergence? Okay. And that's a very important question in mathematics. Okay. Until next time. Bye-bye. Bye-bye.